The next review topic we're going to cover is everyone's favorite, Thevenin's theorem. Thevenin's theorem is used quite frequently in engineering electronics, and it's used a little bit differently than what you're used to, but we're going to go over the initial process of how to do it, and then when we get later on into the course, we will cover how to use it in engineering electronics. So what happens if you need to find voltage, current, or power, and there's a bunch of different resistances connected to the same circuit? This is probably the initial application of Thevenin's theorem that we learned. How do we avoid analyzing the entire circuit a whole bunch of times for those values of resistance? Well, Thevenin's theorem is the answer. First of all, we're going to talk about a couple things that will actually translate into engineering electronics that we're going to talk about frequently. And a few things we're going to discuss is, first of all, what a load is. A load is anything that we use a circuit or some other type of device to power. A resistive load is pretty much anything that has resistance. A resistive load can dissipate or absorb real power. So examples would be a speaker, light bulb, heater, something that we want to supply power. A large load actually means a large current, which would be a small resistance. So a large load is not a large resistance, it's a small resistance. A small load, conversely, is a small current or a large resistance. So that's the first thing we want to get out of the way. The second is what a linear element is. If the relationship between voltage and current is linear, then the element is linear. So resistance is a linear element because the voltage of the resistance equals the current times a constant R, and that R value does not change. Capacitance, even though it has an integral involved in its voltage-current relationship, is still linear. Also inductance, even though it has a derivative, is still linear. These all have linear voltage and current relationships. A nonlinear element would be a diode. We will cover these later, but you'll notice that the voltage and current relationship is not linear. It actually is exponential. So this would be an example of a nonlinear element. You can't use Thevenin's theorem in the part of a circuit that has a nonlinear element. So you can't use it in the part of a circuit that might have a diode in it, but you can use Thevenin's theorem in other parts of the circuit that are linear. And this is one of the things that we do in engineering electronics, is you might have a circuit with a diode in it, and the natural way to analyze the circuit is to Thevenize part of it to make it simpler while looking at the diode. So that's an example of one kind of Thevenin theorem we might do. So Thevenin's theorem is defined as a process in which we can take a complex linear network and we can replace it with a circuit that has one Thevenin voltage source and one series Thevenin resistance, and it provides the same voltage and current to the resistance attached to it that the original circuit. So this makes the circuit much, much simpler. So what is the process? Well, first of all, we take the load resistor off if we have one. Sometimes it's not a resistor. Sometimes it's a whole chunk of circuit we take off. So it doesn't necessarily just have to be one resistor. It's just when we first learn how to Thevenize a circuit, we usually just use one resistor. But you don't have to. You can divide a circuit in half and Thevenize half of it if you want. Then we find R Thevenin. Remember, for finding R Thevenin, we turn off all voltage sources and replace them with short circuits, and we turn off all current sources, replacing them with open circuits. Then we find the equivalent resistance looking into the open terminals left by removing the load resistor. The Thevenin voltage is found by finding the open circuit voltage across the open terminals that are left by removing the load resistor. Then, once we find that, we draw a simple series circuit with V Thevenin as the voltage source. R Thevenin as a resistor in series with V Thevenin. One thing to note, the Thevenin voltage is not ever the source voltage in a circuit. If you have a circuit and the Thevenin voltage ends up being the source voltage, then there was no point in Thevenizing the circuit to begin with. So when the circuit is redrawn, use the open circuit voltage that's found. Don't use something different. Then, after we draw the circuit, we return RL to the circuit if there was one, or if we took a whole chunk of circuit out, we put that back, and then hopefully the circuit is easier to analyze. So our first example is going to be looking at a circuit in which we're going to use a range of resistive loads, and we want to find the Thevenin equivalent, because otherwise we would have to analyze this a number of times. It would be kind of complicated if we were going to want to use several values of resistance. So the first thing we do is we have to take the load resistor and remove it. So that goes away, and we're left with two open terminals. Then, now that we've gotten to this point, we're going to figure out what our Thevenin is. So we're going to take the voltage source and we're going to short it, so you notice that it's gone. And then we're actually going to also look at what is available in the circuit as far as nodes go. And you'll notice that there is a ground node that connects the 20 and the 15K at one end, and then they are also connected to the other end. So this means that they're in parallel, which means our Thevenin is going to be 20K in parallel with 15K, and then we have to add the 10 kilo ohm resistor that's dangling out there to the process, and then when we go through, we find 18.57 kilo ohms is the value of the Thevenin resistance. Thevenin resistance is not usually too difficult. Most students have no trouble with that. The Thevenin voltage, though, is the other part of the problem. So what we want to find is we want to find the open circuit voltage that is across the gap left by removing the resistor. Now, first of all, that 10 kilo ohm resistor, if it has no circuit connected to it, it's not completing a circuit, it's just dangling. And because of that, it really isn't part of the circuit when finding the Thevenin voltage. It's not dropping any voltage, it has no current through it, so it's what I call a dangling resistor. This is only true with finding the Thevenin voltage. With Thevenin resistance, we still use it, but with Thevenin voltage, we don't. So that gets taken out of the circuit, and we basically just move over and find the voltage across the 15 kilo ohm resistor. And this is just voltage division. We can just take 15K over 15K plus 20K times 35, and we get 15 volts. Now we go back and we draw our Thevenin equivalent circuit, and then we add RL back into the circuit, and that will provide us with the same voltage and current that the original circuit did. So that's one example, not too complicated. The second example we're going to look at is going to find power in a resistor that we actually have a value for. So we have two sources, a voltage source and a current source. And what we're going to do, first of all, we're going to remove the load resistor. That's easy. Take that out. And then we're going to find the Thevenin resistance first. So when we look into the terminals, we turn off the sources. So the current source is an open circuit, the voltage source is a short circuit, and now when we're looking at the resistance, we just get 5K. And remember, no dangling resistors when finding the Thevenin resistance, because the actual ohm meter completes the circuit. So the Thevenin resistance is just going to be 2K plus 3K, which gives us 5K. And now we're going to find the Thevenin voltage. With the Thevenin voltage, we have a dangling resistor, so that's not going to be part of the circuit. We're going to get rid of that and move over. And really what we need for the Thevenin voltage is the voltage across the 2 milliamp source. And we can solve this using Kirchhoff's voltage law relatively easily. We're just going to have minus 4 plus 2K times minus 2 milliamps, because the current's going the opposite way of the polarizing marks that are on the 2 kilo ohm resistor. And then we add V Thevenin, and that equals 0. So V Thevenin is going to be 8 volts. We go back, we draw the original Thevenin circuit, and then we're going to add the 1 kilo ohm resistor back. And when we do that, we can now figure out what the power dissipated is. We're first going to find the circuit current to finish the problem. It's series circuit. We just take 8 volts divided by 6 kilo ohms. We get 1.33 milliamps. And then we find the power dissipated by the 1 kilo ohm resistor using I squared R, which gives us 1.33 milliamps squared times 1K equals 1.78 milliwatts. So we will use Thevenin's theorem here and there in the course, and it will be a bit different than what I just covered, but hopefully this at least reminds you of the process.